Our second motivation for why we need a new theory, why we need this crazy quantum theory, it's often referred to as black body radiation. Basically, old school thermodynamics predicted the color that a hot object will glow at based on temperature. So if you've heard of like red hot, white hot, blue hot, um, basically if you take an object that's black and heat it to different temperatures, it will glow at it glows at different colors. So each color kind of had a corresponding temperature. So if it was red hot, that meant a certain temperature. White hot or blue hot would be another temperature. Uh, in your everyday life, when you have your oven going or a toaster going, and that element is glowing red, that's kind of what we're talking about here. That's kind of related to black body radiation. It is a real effect. Things glow at different temperatures when they're hot. As math got better and people got better at experimenting and figuring out what the theory said, what temperature these hot objects should be, and when they did experiments to see what temperature hot things actually were, what this older classical theory predicted was a graph that kind of shot up and off to the moon. But what the world actually did, what the experiments actually did when people did it, they got this really cool kind of swoop up curve like that. So the theory predicted one thing that was completely different than what the outcome of the experiments were. So that's classic. This beautiful theory, this old school thermodynamics can't be right. The ugly fact was this nice looking curve here. That's what the world was doing. This graph that I found, visible is kind of labeled in here. So red hot would be, kind of, if we could shoot this up, red hot would correspond to there. And then Roy G. Biv, violet would be way over here. So the intensity, how much light came off. So basically we got one graph when theory predicted a completely different graph. Still going on with the idea of motivation. This was a huge deal in the late 1800s because of what had just been invented. Thomas Edison had just patented, lots of people were working on it, so there's cool stories about that, but Thomas Edison perfected it. He patented the incandescent light bulb. The incandescent light bulb is all about getting something hot so that it glows and gives off light. When you learned about incandescent light bulbs way back in elementary school science, the whole point was incandescent light bulbs aren't very good because they give off too much heat. They're not efficient at creating light. They're creating this other stuff. Well, the other stuff is just infrared light outside of our visible, so it is a waste. We don't need it. So the motivation was, if we could get an incandescent light bulb that didn't give off all that infrared heat and just gave off regular Roy G. Biv light, so just gave off that little sliver of Roy G. Biv, then incandescent light bulbs would be more efficient. At the time in the late 1800s, people were developing our electrical grid, like building power plants at Niagara Falls, trying to get electricity out to cities. So they were all kind of connected. We've got this cool invention that everybody wanted, but it was quite inefficient at doing the job it was supposed to do. It was designed to make light, but it was making a whole bunch of other stuff, infrared heat. So, rather cleverly, the German government had a great idea. They hired one of their best people to study this whole black body thing and see if they could improve the incandescent light bulb. See if they could get rid of the infrared so that it just gave off Roy G. Biv, then it'd be way more efficient. So imagine like an incandescent light bulb, but it only gave off light, so it didn't get hot. You could touch it and not burn yourself. That was their goal. And it makes really great sense. The whole downside to this cool technology was giving off too much heat. So let's try and make a better one of those. The person that they hired, you heard about this guy if you've already done the lab, was a guy named Maxwell Planck. Crazy smart guy. As he's trying to solve the problem, he comes up with a brand new theory of light energy. It matched the experimental graph, so it's good, and it looked different. It looks so simple. He said that the energy of light is proportional to the frequency. Or to go from a proportion to an equation, we have to add a constant. So the energy of light is some constant. If we were to do this as a lab, the constant would be like the slope, kind of like those labs we did at the beginning of the quadmester. After the fact, they named that constant after him, so it's called Planck's constant. It's got this value here, this crazy small number, 6.626 times 10 to the negative 34. To make the units work, it has to have joules on the numerator and seconds on the numerator, since frequency is seconds on the denominator. That simple equation, E equals hf, describes the energy of light. It matched experiment, and it changed physics forever. Basically, what that little equation did is it quantized light. What Planck is saying is if we have a beam of light or a source of light that's giving out only one color, so one frequency, you could plug in a number like 600 nanometers. If you plugged in 600 nanometers, put it in meters, multiplied 600, and once we put it in meters, multiplied it by h, you're going to get a crazy small number and amount of energy. But what his theory, what his equation is implying, is that all 600 nanometer light is delivered in energy amounts that are multiples of whatever E equals h times f multiplies out to be. So let's say that number works out to be 4 with some crazy times 10 to the negative something. If that was the value that orange light gave, you could have orange light that had energy of 4, orange light that had energy of 8, orange light that had energy of 12, but never 6 or 5 or 9. It could only ever be delivered in multiples or bundles of whatever E equals h times f works out to be. That is the birth of quantum. It's the quantization, it's the bundling of energy. Planck was a smart guy. His work was sound. There weren't any flaws in his theory. And when they did these black body radiation experiments, it matched the experiment. So we've got a good theory with experimental verification that says energy of light is related to the frequency of light. That's kind of treating light as little particles that deliver energy. So each little bundle of orange light, they started calling these little bundles particles of light. They started calling them photons. Each photon of orange light is going to deliver a certain amount of energy. You could have 2 photons or 3 photons, therefore multiples of that base amount of energy. Here's the problem. In the early 1800s, the last unit we tackled, Unit 4, it was all about the wave model of light. Thomas Young did some great work. He had a great experiment to back it to show that interference of light. The only way to explain the interference of light is to treat light as a wave. That's the only explanation. And if we're treating light as a wave theory says energy is related to amplitude. So here's our huge new problem. There's now 2 models of light. The one we learned last unit was the wave model. We did an experiment. You guys saw the double slit experiment. So it's on paper it looks good. It's experimentally confirmed, and it is based off the idea that energy is related to amplitude. Planck came along, solved the black body radiation problem, created what we're going to call the particle model. The particle model is also experimentally confirmed. The black body radiation experiment shows that it's right, but it has a completely contradictory outcome. It says that the energy is proportional to the frequency or the color. If you're doing things in order, you already know the answer. Einstein actually came up with the idea when he won the Nobel Prize way back in 1921. When he won the Nobel Prize, he kind of cited the photoelectric effect as one of the cool things that Einstein came up with. If you haven't done it yet, I'm not going to tell you the outcome. You got to discover it. Go to Lab 5.1. There's a description of the photoelectric effect there. Do that wee little lab. You'll discover which one is right, wave model or particle model. In theory, you've done that already if you're following along and keeping up. Instead of doing the next part of the lab, just to make life a little bit easier, jump to topic 3 next, and that's going to explain the outcome of the lab.